Welcome back to CST432 Microprocessors and Embedded Systems. This is NXT Anthropology. First, some background. The NXT originally started with the Robotic Immersion System, or RIS, an RCS brick which uses an 8-bit Hitachi microprocessor. Now, the MINDSTORM NXT uses a 32-bit Atmel AT91SAM7S256 microcontroller for its processor. Now, we would like to see in this module the evolution of register and memory architectures to better understand the ARM CPU core that is used in the MINDSTORM NXT today. Some key concepts that we will cover in this module is, first of all, what is register file design? Secondly, what are instruction operands and addressing modes that can be used for a given processor? And then we will look into how the ARM architecture implements this register file design as well as ARM instruction operands and addressing mode. As we go through this module, maybe we would like to keep some questions in our mind. First, why do accumulator architectures need to specify a memory location as one of its operands? Secondly, what is the advantage of using stack-based architecture? And third, what are the bank shadow registers in ARM used for? We will first look at register file design. There are several register file designs that have been in use through the history of microcontrollers. First is the accumulator architecture. Second is the register memory architecture. Third is the register or load store architecture. And finally is the stack-based architecture. The accumulator architecture is found in the earliest microprocessors and microcontrollers. In this architecture, we have an ALU, or arithmetic logic unit, which performs the arithmetic calculations. We also have an accumulator, otherwise known as a register, that is used to store the results. In addition, we will have to have a means of accessing memory locations. Typically, this is found in a address index pointer register, which is used to indicate the address location that we want to retrieve from memory. And of course, we will have access to memory addresses or memory locations in the storage space. Now, the accumulator architecture has very limited capabilities. The register memory architecture builds upon the original design to add additional accumulators for storing intermediate results of calculations. And the ALU will be able to retrieve the value from either the accumulator or from memory to perform its calculations. In addition, we may want to have multiple index registers to reference different blocks of memory, for example, to be able to copy one block of memory from one location to a different location, and we will use a second index register to point to this new location. Now, what happens if you want to expand the number of values that we can store in the CPU without affecting the access to memory? The reason being that access to memory is slow. It takes time to retrieve a value from a memory location compared to if we have it already inside one of the registers. So this design is the register architecture, otherwise known as a RISC architecture. In the RISC architecture, the fundamental concept is that there are a lot of built-in registers, shown here as general purpose registers 1 to n, and maybe a value of 16, 32, or even higher depending on the CPU. Now, the ALU will perform its operation only on values stored in these registers. It will not retrieve any location from memory as an operand for an instruction. Instead, the only way that the register architecture retrieve or access to memory is through means of special instructions such as load and store. Finally, we have a rather interesting architecture called stack-based architecture. In this architecture, there is no registers found in the CPU at all. Instead, there is an ALU as well as a stack pointer which accesses to memory locations. And the stack pointer performs its operation by retrieving values from a stack which is defined in memory. So the stack pointer retrieves the topmost items from the stack and bring it into the ALU, as well as the next topmost item from the stack. And these two operands will then be added or subtracted, or some other arithmetic operation performed upon them, and finally the result will be stored back into the top of the stack in memory. Based on the register file design we have studied previously, we can then come up with various instruction operands and addressing modes of those operands. The first instruction operand mode is the inherent or implicit addressing mode. Second is register locations. Then we have immediate or constant values as operands. We also have direct or fixed addressing operands, as well as indirect or pointer-based addressing operands. We should also note that the number of instruction operands differ from processor architecture to processor architecture. But typically, the CISC microcontrollers or microprocessors uses 2 operands. So if you have addition of A, register A or operand A with operand B, the output of this calculation will be stored back into one of the registers, typically register A. Now if in the RISC processor, we define 3 operands typically. What this means is that we are able to perform an operation or calculation on 2 registers A and B, and the result can be stored into a different register C. So what is inherent addressing mode? In this mode, there are no operands specified for the instructions, or otherwise they are known as zero operand instructions. This does not need to refer to memory, or else the addressing is implicit. Example of this is a no op instruction, which does not change the state of any of the registers in the microcontroller or microprocessor. And then there's the return instruction, which returns execution to the routine, which called a subroutine. And this instruction uses an implicit address stored in the stack or in a link register. Now the next type of operands are register location operands. These refer to registers locations found in the microprocessor only. And the register name will depend on the microprocessor that we are referencing. So in this examples given here, we are using the Intel ADX86 architecture to illustrate this example of register locations, and the instructions here are increment AX, which is one of the registers in the Intel processor, and the second instruction move is actually a copy of the value from the register BX into the register AX as the destination of this instruction. Another type of operand are constants or immediate values. They are used for operands in order to initialize or to set the register to a known value. And they can only be used as a source operand because we cannot modify a constant value by definition. So example of this is the move instruction from using the constant value 13E hex into the register AX. The next type of instructions operands are the direct addressing mode operands. This refers to memory address locations explicitly as part of the operand of these instructions. Now this is not available in register-to-register architecture such as RISC processors normally. In this type of instructions, what we do is that we have the address of a memory location specified as part of the operands of these instructions. An example here is the move instruction, which copies the value in register AX into memory location given by 200 hex, and we represent the direct addressing mode address using the square brackets to represent a memory address instruction. The next type of instruction operands using indirect addressing mode gives us a lot of flexibility. Instead of referencing a memory address location explicitly as an operand of an instruction, we will use the register to store the memory address location value. Using the register as a pointer, we will then be able to access the instruction, the memory location, without having to use a different instruction for every location. Instead, we update the value in the register to a new location. So different types of indirect addressing mode exist depending on the microprocessor features. In this example here, we have 2 instructions, move AX, square bracket BX, which copies a value from memory given by the address in BX into the register AX. The next instruction, move BX in square bracket plus offset 5 and comma AX, will then store a value from AX into the memory location given by the address pointer value in BX with an additional constant offset of 5, meaning a location that is 5 bytes away from the current address pointer location BX, and store that value there. What these 2 instructions have done is to take a value from one location in memory and store it 5 positions away in memory again. Here we'll look at the ARM register file design. As you can see, this diagram is a bit complex, but we'll break it down one by one. First of all, we notice there are several processor modes. We have the user and system modes, then we have the fast interrupt mode, the supervisor mode, the abort mode, the interrupt mode, as well as the undefined modes. These different modes of the ARM processor allow us to perform or separate the execution of programs that are user programs from the kernel or OS level programs. First, we look at the system or user state. We can see that there are 16 registers R0 to R15 defined in the system and user state. Now, R15 is actually a dual purpose register. It is a program counter, but it also references R15 in order to allow us to use various arithmetic and logic functions to manipulate or update the value in the program counter. In addition, there is also a current processor state register or CPSR, which is used to store the status flags of various arithmetic operations as well as the current execution state of the processor in this register. Next, we see the fast interrupt mode registers. Actually, the registers R0 to R7 are shared with the other states. In other words, they are the same registers, it's that they are represented here in a separate column. Now, the subsequent registers with the shaded triangle are what is called bank registers, meaning that they only exist in that mode, which is the FIQ mode. The FIQ mode allows us to service interrupts in a very quick manner because the bank registers are additional registers that are unaffected by any changes in other modes. This allows us to perform some quick interrupt processing without upsetting or changing the values in other registers. If we have to change values in other registers, we will have to preserve them on the stack somehow, so that when we return from the interrupt, they will not be modified. So by means of use of these bank registers, we have the means to perform a calculation without affecting the non-banked versions of these registers. In addition, there is also a SPSR, which is used to store the previous execution state of the processor, so that when we return from the interrupt service routine, we can restore the state of the CPU to its original state. The supervisor mode is similar to the fast interrupt mode in that it is a special or privileged execution state. However, there are only two bank registers. In other words, they share all the other general purpose registers with the user mode. However, the use of these two bank registers allow us to keep a separate stack for supervisor mode and as well as a separate link register, so that we can call other routines from within supervisor mode without affecting the user mode program. Here we see the details of the program status register or PSR registers. The two versions, the CPSR and SPSR, are similar, except that the CPSR indicates the current operating status, and the SPSR indicates the previously operating status that was interrupted when we entered into the privileged execution mode. The most significant bits of this PSR register contains the condition flags, or else known as the status flags of that's updated by arithmetic and logic instructions. So it's the negative flag, zero flag, carry flag, and overflow flag. The least significant bits contain the state or status mode bits of the processor, which indicates the current operating mode that the processor is in, whether it's supervisor or user mode, interrupt mode, and so on. Finally, there are two interrupt mask bits that allow us to control whether the processor will be interrupted by any external interrupt signals. Now, the presence of so many registers require the use of a standard or a convention for how we can make use of these registers in a consistent manner. This is defined in the ARM Architecture Procedure Core Standard, or AAPCS, for use by any compliant ARM routines or programs. Now, in this standard, the registers have been classified into various groups so that we know how to make use of them. The first four registers, R0 to R3, are what is called argument registers. They are used to pass arguments from a routine to a called subroutine, and they are not preserved, meaning that they do not need to be maintain its existing values upon return from the called routine. In addition, R0 is also used to provide the return value from the routine to the parent routine. The next group of registers, R4 to R11, are routines or registers that need to be preserved when you use it inside a subroutine. Now, in general, they can be used for any purpose, but some of them may have specific definitions depending on the platform and operating system that is used. One example is R11, which is used as a frame pointer by the C compiler GNU GCC if it's defined to use a stack frame pointer. Lastly, the group of registers R12 to R15, although they are general purpose registers, have specific functions within any ARM program. R12 is normally used as an intra-procedure call register, and it does not need to be preserved. However, R13 is typically used as a stack pointer and must be modified carefully, otherwise it will cause the stack corruption to occur. R14 is known as a link register, which is used for subroutine calls, and it stores the return address so that we can return execution to the calling routine. Finally, R15 is the program counter, and this must not be modified unnecessarily because it will affect the execution of the routine or program logic. We will now look at the ARM addressing modes available. First, there is what is known as ARM Mode 1, which covers the immediate and register addressing modes we have studied previously. We see that in ARM addressing Mode 1, the immediate values are what is called scale immediate constants, which comes from a restricted range. What this means is that if you want to specify a constant as an argument or operand to an instruction, we can only take it from a specific range of values. It is not possible for us to define 32-bit constant values, for example. There are different ways of addressing this issue in our code, which we'll talk about another time. For register operands, we can either reference to registers, or registers can be modified by a shift or rotate, optional shift and rotate argument, which allows us to convert the value of the register into a modified version for use with our arithmetic calculation. Now, ARM Mode 2 is used for indirect addressing. Now, ARM Mode 2 is used for word and unsigned byte indirect addressing, as well as unsigned byte and indirect addressing with offset. Now, the offset can be specified as an immediate value, or else it can be found in the second register to be used as an offset to be added to the primary indirect pointer value. There is also ARM Mode 3, which is used for indirect addressing. The difference between ARM Mode 2 and Mode 3 is that ARM Mode 3 is used for half word and signed byte indirect addressing only. The range of values used for the immediate offset is limited, as well as the combination of offsets using registers are also limited in ARM Mode 3. Finally, there is ARM Mode 4, which is used for multiple register, load and store, or else known as vector indirect addressing. We shall now look at some examples of ARM instructions for each of these addressing modes. First of all, we note that there are no inherent addressing mode instructions in the ARM instruction set, because we do not have any instructions that do not need to specify either a constant or a register operand. For register allocation operands, we have these given examples: add R0, R1, R2, which is to add the value in register R1 with register R2, and then store the results into register R0. The format for ARM instructions is that the first argument to an instruction is always the destination register. The second instruction, move R4, R1, will copy the value in R1 into register R4. The next instruction, branch exchange, BX, R2 uses the value in R2 as the address to perform the branch and exchange instruction with. And finally, the test equivalent, R10, R3, will compare the value in register R10 with the value in register R3 and update the status register flags itself. The next type of operand is the immediate addressing mode operands. In this case, the constant value must be specified using a hash or a pound sign. Move R1, hash 5 will set register R1 with the constant value 5. Branch or B label uses the address location of the target label as the argument to the branch instruction. Compare R9, #0 will compare the value in register R9 against the constant value 0 and set the flags accordingly. We note that the ARM processor also does not have direct addressing mode instructions. This is because we are not allowed to access memory operands directly from most instructions. Instead, we have what is called indirect addressing mode instructions, which are the load and store instructions used for accessing to memory. Load LDR R3, square bracket R0, close square bracket, indicates that we take the contents of memory address location given by the pointer value in R0 and retrieve it into register R3. Now the load instruction takes 32-bit values from memory, so it will take it from the address starting from the value in R0 and the next 3 memory address locations as well. Store byte or STRB R7, open square bracket R1, close square bracket, will take the value in R7, 8-bit value, in the least significant byte of R7, and store it into the memory address given by the address in the value in register R1. Load register R0, open square bracket R3, R4 is an indirect addressing mode which uses R3 as a pointer and R4 as the offset value to be added together in order to come up with the effective memory address location. The next group of instructions are the vectored addressing mode instructions. In this instruction, the store multiple STM has also a suffix which is given here as FD, full descending, is used to access the registers R0 and R7 to be stored into memory given by the value in the stack pointer SP. The load multiple with full descending instruction LDMFD will take the values from memory given by the address pointer SP and store them into the registers R1, R3 and R9 given by this instruction. Of course, we can have some combination addressing mode instructions as well. First example, add R1, R2, #5 will add a constant value 5 to R2 and then storing the result into register R1. Subtract R0, R3, R7, LSL-2 will modify the value in R7 by shifting it left by 2 bits. Now this left shifted value is equivalent to multiplication of the R7 value by 4. So what happens in this instruction is R3 contains a value that is subtracted, will subtract the value in R7 and the result will be stored into R0. Next example, subtract R0, R3, R7, ASR, R1 will cause the value in R7 to be shifted right arithmetically by the number of bits stored in the register R1. So R3 minus this value will be stored into R0. Load register R0, R9, #10 will take the value in memory given by the address pointer R9 with an offset of 10 into the actual memory address, and then taking that memory contents and loading it into register R0. Load byte will take an 8-bit value only from address location R3 minus R2, which is taken as the effective address of R3 minus R2, and then storing the value into register R1. Finally, store R7, R3, R2, LSL2 will take the value in R7 and storing into memory location given by the calculation of the effective address given by R3 add to R2 left shifted by 2 bits. Okay, so to conclude, there's some additional questions to think about. First, how many operands to each type of register file architecture is typically required? Secondly, what are examples of stack-based programming languages? You may want to look up the reference there for more information on this topic.